In this video, we're going to go through combined gas law. In the previous lesson, we looked at ideal gas law, which takes the format PV equals nRT. So pressure and volume are proportional to the number of moles times our constant R, and then the temperature. And remember, the temperature has to be in Kelvin. Okay, so for combined gas law, we're going to make some assumptions here. So if the pressure, volume, or temperature changes, but the number of moles remains the same, the combined gas law equation can now be derived from ideal gas law. So, again, the number of moles is going to remain the same. So, in our original ideal gas law equation, if the number of moles remains constant, and also our constant will obviously remain constant, if we put them on one side of the equation and then put the things that are changing, pressure, volume, or temperature, on the other side of the equation, we end up with this. Okay. Now, pressure, volume, or temperature are going to change. So we are going to have initial temperature, volume, or pressures. And then we could do the same thing. We would have another equation. Again, we're going to put the number of moles and the constant R on one side of the equation, and we'll put the things that are changing on the other side of the equation. Again, pressure, volume, and temperature. And because we're having an initial and a final, we're going to indicate final pressure, volume, or temperature with a subscript F. Now, because the number of moles and the gas constant are the same on both sides, we can now set these equations equal to each other. So all of the initial values are going to be equal to the final values, or they're going to be proportional to the final values, rather. Okay. So again, the number of moles are not changing. So let's look at an equation where this is going to come into play. So in this example, it says a cylinder of gas is kept at a constant volume. As the temperature increases from 24.1 degrees Celsius to 326.4 degrees Celsius, if the initial pressure is 1.01 atmospheres, what's the final pressure in millimeters of mercury? Okay, so let's set up our equation. So we have PV over T. These are all of our initial values. And we're going to set that equal to PV over T. And these are going to be our final values. Now, a couple important things to notice from the equation. So it says constant volume. So that means the volume's not changing. So if the volume is the same on both sides of the equation, we can eliminate volume from our equation because it'll be the same. The numbers will cancel out. Okay, so here's our new equation. Now, it's asking for the final pressure. Final pressure. To get the final pressure by itself, we're going to multiply both sides by the final temperature to clear that denominator. So when we multiply both sides by the final temperature, it will cancel out on the the right-hand side, and our equation will now be, not TF, PF is going to be equal to our initial pressure, our final temperature, and then our initial temperature. Okay, so let's go ahead and set this up. So our initial pressure is 1.01 atmospheres. Okay, now our change in temperature, we are going from 326.4 and it's increasing 24.1 degrees Celsius. So let's see, we could write it out this way. Our final temperature is 326.4 degrees Celsius, but remember, to convert that to Kelvin, we're going to add 273. And then in our denominator, we're going to have our initial temperature, which is 24.1. And we are going to add, oops, not 24. Wow. Somebody needs to get some more sleep. 24.1 plus 273. Okay, so here's our setup. So let's go ahead and put this in our calculator. and you should end up with a value of 2.04 atmospheres. Okay. The equation is asking for it in millimeters of mercury, so we would just need to convert this. 1 atmosphere is equal to 760 millimeters of mercury. Okay, so we end up with a value of 1.55 times 10 to the third millimeters of mercury. Okay, so the conversion is on the formula sheet for AP Chemistry. So if you don't know off the top of your head that 1 atmosphere is equal to 760 millimeters of mercury, don't worry about it. It's on the formula sheet. Okay, let's move on to Dalton's law of partial pressures. Now, in 1803, Dalton stated, for a mixture of gases in a container, the total pressure exerted is the sum of the pressures that each gas would exert if it were alone. So we sum up all of the pressures, and that equals the total pressure. So let's look at an example where this comes into play. So it says 100.8 grams of oxygen and 289.8 grams of nitrogen are pumped into a 6-liter scuba tank that is kept at 20 degrees Celsius. Find the partial pressure of each gas, and then find the total pressure in the tank. All right, well, let's start by finding the pressure of each gas. So to find our pressures, we're going to need to figure out moles. And we're going to be using ideal gas law, so PV equals nRT. So let's start with nitrogen. To find the pressure of nitrogen, we're going to need the number of moles of nitrogen. So let's first convert our grams of nitrogen into moles. So 289.8 grams of nitrogen. Molar mass of nitrogen into 28.02 grams of nitrogen. That's how many grams are in 1 mole of nitrogen. And we end up with 10.34 moles of nitrogen. So if we set this up using the equation PV equals nRT, we're trying to find the pressure. So pressure is going to be equal to nRT over volume. So our moles, we've got 10.34. We're going to use our constant, so 0.0821. I'm going to leave the units off just because it's a lot to write. And then our temperature in Kelvin, so 20 degrees plus 273 is going to be 293 Kelvin. And then I'm going to put that over the volume of the container, which it says in the question is 6 liters. Okay, so when I plug this into my calculator, I end up with a value of 41.5 atmospheres. Okay, so that was for nitrogen. We're going to do the same thing for oxygen now. So we've got, for oxygen, it's 100.8 grams of oxygen. We're going to multiply that by oxygen's molar mass. So O2 is 32 grams of oxygen in 1 mole of oxygen. So we end up with 3.150 moles of oxygen. Okay, again, we're going to use PV equals nRT, same setup. Pressure is going to be equal to the number of moles times our constant times the temperature in Kelvin over the volume. So we've got, let's see, 3.150 moles. We're going to use the same constant, 0.0821. Temperature is the same, 293 Kelvin. And then we're going to put that over the volume of the container, which is still 6 liters. And we end up with a value of 12.6 atmospheres. So for part A, our pressure of nitrogen is 41.5. Our pressure of oxygen is 12.6. Now to find the total pressure in the tank, so for part B, we are going to add those values together. So the total pressure is going to be equal to 41.5 atmospheres plus 12.6 atmospheres. So if I combine the two pressures, I end up with a total pressure of 54.1 atmospheres. Okay, so again, Dalton's pressure equation, we just add up all the individual pressures, and that will give us the value of our total pressure. And that's it.